Welcome to Science View. I'm your navigator, Tomoko Kimura. Science View covers the latest advances in Japanese science and technology. This week's Science Watcher is joining us for the first time today. Dr. Yoichi Sato, professor at the University of Tokyo's Institute of Industrial Science.
Hello, I'm glad to be here. I work in the field of computer science, focusing on computer vision and image understanding.
We're delighted to have you join the team.
Thank you.
Now let's move straight to today's Leading Edge. Plans for the International Linear Collider, ILC for short, have been gaining attention. The ILC is a massive 30-kilometer-long device that will be built 100 meters underground. Its equally massive mission is to probe the mysteries of subatomic particles and the origins of the universe. The Kitakami Mountains area in Japan's Tohoku region is the leading candidate site for the facility to be built. Today on The Leading Edge, we report on a science mega project, the International Linear Collider. And today's science news focuses on a very interesting related topic. Dr. Sato?
That's right, Tomoko. It's about the Nobel Prize in Physics. On October 8, 2013, it was announced that the winners are François Englert of the French-speaking Free University of Brussels and Peter Higgs of the University of Edinburgh in the UK. The award ceremony will be on December 10th. They were awarded the prize for their prediction of the existence of Higgs boson, a new elementary particle. A half-century later, experiments confirmed their prediction, and the Nobel Prize followed that.
The discovery of the Higgs boson last year was widely reported. I remember seeing it on the news.
The Higgs boson was discovered in a device at the European Organization for Nuclear Research, or CERN. The CERN Accelerator Complex is a huge ring, 27 kilometers long. It will take about 6 hours to walk around it. The ILC that we are talking about today is planned to be about 30 kilometers long, running in a straight line.
And it will continue the research for undiscovered elementary particles that could lead to further Nobel Prizes even.
If new particles are discovered, that's quite possible.
Let's start by taking a look at the massive European facility so crucial to the Nobel Prize Award.
We have a success today. We have a discovery. We have discovered a new particle, a boson, most probably a Higgs boson.
July 2012, news of the discovery of the Higgs boson broke around the globe. The Higgs boson was discovered at CERN in Geneva, Switzerland. CERN has a dedicated staff of 2,300. In addition, each year more than 10,000 researchers from more than 50 countries are involved in the research that takes place here. The device that spotted the Higgs boson occupies a ring 27 kilometers around. Inside the ring is a device called a particle accelerator. Protons are accelerated to close to the speed of light and smashed into each other, releasing a huge burst of particles that scientists analyze. It was among these particles the Higgs boson was spotted. What is a Higgs boson? We need to dig down to an almost unbelievably tiny scale to arrive at the elementary particle, a particle that cannot be divided further. Over the past 100 years, physicists have been researching elementary particles, concluding that there are 17 of them in all. Of these 17 elementary particles, only the Higgs boson had never been observed. The Higgs boson is thought to be deeply connected with the birth of the universe. Immediately after the Big Bang created the universe, massless elementary particles were hurtling around at the speed of light. Later, as the universe expanded rapidly, it also cooled. The universe changed state, something like when water freezes to ice. When this happened, Higgs bosons started snagging on other elementary particles. It became more difficult for particles to move, so they slowed down. This was the origin of mass. The Higgs boson was important in causing elementary particles to acquire mass. July 2012. The announcement that the Higgs boson had been found sparked thundering applause. Dr. Peter Higgs, the scientist who predicted the particle's discovery half a century ago, was present.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
What a powerful moment for Dr. Higgs to have his prediction confirmed after 50 years.
Yes, the Higgs boson is an elementary particle that generates mass. You could say that it is why we have matter and the universe as we know it. The discovery of the particle is critical for supporting the theory.
But even though we found the Higgs boson, which was the last unobserved particle, that doesn't mean physicists are done with it, right?
Although the Higgs boson has been found, its properties have not been precisely determined yet. The researchers need ILC to study it in more detail.
And how will the ILC be different from CERN?
Well, it will be linear rather than ring. It will also collide different particles. The CERN particle accelerator collides bunches of protons together to create various observable reactions. It excels in observing large numbers of reactions. But the ILC will collide electrons and positrons together. The mass of an electron is over 1,000 times less than that of a proton. The ILC will allow detailed observation of the phenomena resulting from the collisions. It will also be used to study Higgs boson in detail.
Are there any other research results expected from the ILC?
Solving mysteries of the universe. The elementary particles all around us account for only 4% of the energy that makes up the universe. What is the other 96%? Recent research has pointed to things called dark matter and dark energy. Dark matter is said to account for about 23%, and dark energy 73%. But scientists don't know much more than that. The ILC could shed light on that mystery.
It's surprising that we only know about 4% of the energy in our universe, but we can be hopeful that the ILC's experiments will help unravel the mysteries behind the remaining 96%. So now let's look at details of how the ILC is planned to work.
June 2013. The completion of the technical design report for the International Linear Collider is announced. This document contains the details of how the device will be built. It is the work of more than 1,000 scientists over a period of more than 8 years. 3 sites around the world were hooked up by video conference to celebrate the milestone.
Hi, Brian on the hall in Geneva. So we are going to do the handover. Okay, I'll hand you over the button. Okay, here he goes. Here he goes.
The report gives a clear picture of how the ILC will operate. It will be built 100 meters underground. Its total length will be approximately 30 kilometers, running in a straight line, hence the name linear. From opposite ends of the collider, negatively charged electrons and positively charged positrons will be shot toward the middle. Accelerated to near the speed of light, they will collide head-on in the middle, hopefully producing as yet unknown particles and phenomena. But where will this massive facility be constructed? In August 2013, a group of researchers associated with the ILC announced the candidates. The news drew extensive media attention.
The ILC Site Evaluation Committee has considered the technical, social, and environmental factors and decided unanimously that the Kitakami site is the best suited to be Japan's candidate for the ILC.
Municipal government representatives watched the announcement anxiously. The committee chose the Kitakami Mountains in the Tohoku region. Its stable, hard bedrock geology made it attractive. On October 17th, a survey delegation toured the candidate site in Kitakami.
So the access point is just over that way.
In the delegation are researchers involved in planning the ILC, as well as local government personnel.
Absolutely. Okay. Absolutely. Well, I think it's much better than looking at a map. I think we can really see now what is possible, and I think it's a very good site.
The final decision on where to locate the ILC will be made after negotiations among the countries involved.
So the ILC project has finalized its technical design report and narrowed down the candidate sites now.
In fact, preliminary planning for the ILC project has been going on for many years. The idea was first raised in the 1980s. In the 1990s, Japan, the US, and Europe were all pursuing independent efforts.
So it's a project physicists have been considering for more than 20 years.
From the year 2000, there was growing interest in joining forces amongst the US, Europe, and Japan. Researchers from around the world got together, and in 2005, the ILC was launched as an international project. Now in 2013, we have the technical design report and a short list of possible sites ready.
That's quite a long process. So now that we have the technical design report, we have a more detailed picture of the whole project then.
Yes, there will be international negotiations over the next 2 or 3 years to decide where it will be built. An international research organization will be founded to run it, and construction will take 10 years or so. At the earliest, the ILC could be completed and begin operating in 2028.
It's certainly an ambitious plan, and it sounds like this is a critical juncture in its progress.
Yes. Although the ILC will not be finished for decades, in Japan, researchers are already working on developing a technology for it. Let's take a look.
This is Japan's High Energy Accelerator Research Organization, known as KEK, in Tsukuba. At this facility, research on the electron beam that will be used in the ILC has been going on since 2001. A team of 70 researchers from 20 countries are assembled here to conduct the research effort. The distance traveled by the electrons and positrons from each end of the collider to the center is about 11 kilometers. It will require exceptional precision to direct the beams to meet right at the center of the detector. Experiments are underway on how to do this as efficiently as possible. Once a year in September, the facility holds an open day, at which the public can view part of the experimental apparatus. This is the beam line. It is 60 meters long and squeezes an electron beam down to a width of a few nanometers. The beam is composed of a series of bunches of electrons. Each bunch contains about 20 billion electrons. Magnets are placed along the pipe through which the electron bunches travel. These magnets compact the electron bunches down to very small dimensions. Having a higher density of electrons in the bunch makes it easier to collide them successfully. So far, researchers have achieved 80% of the target density.
We're studying how the magnets should be tuned, where they should be placed, and how they should be controlled as part of developing technology to shape an ultra-compact beam.
They are also working on another challenge: how to actually manufacture the collider. Most of the ILC will be composed of accelerators for the electrons and positrons. These devices, which look like stacked dishes, are superconducting RF resonant cavities. Made of a special metal called niobium, which can behave as a superconductor, they allow electrons and positrons to be accelerated efficiently. This disc is the raw material for making a superconducting RF cavity. Each one is carefully stamped into the proper shape. These metal dishes form the cavities. They are stacked in an alternating arrangement and welded together. The weld greatly affects the performance of the resonant cavities. The welding is done under vacuum with an electron beam inside a special device. In one corner of the laboratory is a cabinet. It contains samples made using the electron beam at various power and speed settings. These experiments are to determine the most consistent weld.
Each cavity is very expensive, and if the final weld is not perfect, then the cavity has to be thrown out. So we are doing a whole series of experiments to figure out what parameters give us the flattest, smoothest, most consistent weld. It's a critical task.
Research is continuing to determine the most efficient way to build the superconducting RF resonant cavities for the accelerator.
They're already making incredible progress in preparatory research for the ILC.
Yes, research on the core technologies seems to be going very well. In order to build the real thing, they'll need to make 16,000 of those superconducting cavities. Some Japanese companies are already making preparations to mass produce them. Mihara, a city in Hiroshima. This Japanese manufacturer has been making particle accelerators for 50 years. This precision tool machines accelerator parts. It has a diamond cutting blade that can shave off ultra-thin layers of material. Look how shiny it is straight from the machine, with no polishing. It has to be totally free of imperfections. The completed parts are then meticulously inspected using three-dimensional measuring instruments. The precision is a thousandth of a millimeter. Not the slightest blemish is overlooked. Now they are studying how to mass-produce parts while maintaining this exacting quality.
I see. The accelerator itself is huge in scale, but the parts have to be made with extreme precision. To shoot such tiny elementary particles from opposite ends of a 30-kilometer device and get them to collide, you need this level of technology. And so, how much is all of this expected to cost?
The ILC itself has been estimated to cost 830 billion yen. Usually with such huge projects, the host country would pay for half of the construction cost, and other participating countries the other half. With the ILC, the allocation will be decided in the country-level negotiations to be held from now. Since Japan has KEK, where R&D on the core device is underway, and manufacturers are preparing to mass-produce parts, many researchers are now hoping to see the ILC built in Japan. The question would be where to get such huge funding.
And what would be required for Japan to build it?
If the ILC were built here, it will require a huge commitment of tax money. So it will be important for the project to have the support of a broad spectrum of the population. Now researchers are working to build that support.
Recently, a symposium was held in Tokyo. Discussions focused on research to reveal the mysteries of our universe and the possible impact of the ILC project on Japanese society. Let's take a look.
October 15th, a symposium at the University of Tokyo's Ito International Research Center. Accelerator researchers organized the symposium entitled "Can the ILC Solve the Mystery of the Universe? The International Linear Collider Project." The event was hosted by Akira Ikegami, with a panel comprising Hitoshi Murayama, Lynn Evans, Mike Harrison, Naoko Yamazaki, and Yukako Uchinaga. The panel discussion touched on how the ILC could draw a large community of foreign researchers and create a new global city.
There is a lot of debate about how Japan nurtures people ready for global interaction and how engaged Japan is with the world. This project will bring a large number of people into Japan. To what extent will Japan be able to accept global standards? That's an issue.
In this case, the issue is rather how 10,000 people from other countries are going to live alongside Japanese people for an extended period, 10 or 15 or more years, as they work with us to build the ILC. As a Japanese person, I see this as a wonderful opportunity for globalization. I call it globalizing at home.
What are the key issues for welcoming people here then, do you think?
When Japanese people haven't had much experience with it, they can be hesitant about interacting with people who have different cultures, speak different languages. But if those people were living right near them, mindsets would change. If there were even one place in Japan with an environment like that, it would be like the catchphrase, "Study abroad without leaving town." Japanese people would get used to that setting and realize what the expectations are when they go to other countries. We would have more people ready to venture out into international society. It would be training in a new mindset and culture.
I think Japan is it's a modern industrialized society. It has a distinguished history. It has a unique culture. It has all of the fundamental requirements to support a community of scientists. I think one needs to provide an environment that gives you a balance of the local culture as well as the social interaction amongst themselves that the science community needs.
Yes, well, I think the problems are no different in Japan to any of the other great laboratories in the world, be it in Fermilab in Chicago or CERN in Geneva. And these problems have been solved over the years. It may not be immediate, but I'm quite sure that Japan can certainly, and the Kitagami region will certainly evolve to take into account the needs of the internationals.
People are talking about Japan globalizing in various ways, about work-life balance. These keywords are being bandied around a lot. But on the other hand, many non-Japanese coming to Japan might be the catalyst for some reassessment of Japanese society, and then moving Japan forward in a positive direction. I'm hopeful of that.
Researchers hope that further events like this symposium will deepen public understanding of the ILC plan.
Dr. Sato, what else was covered during the symposium?
There was discussion of how technologies developed for particle accelerators are being applied in various industries. Particle beam therapies for pinpoint cancer treatment, tools for developing drugs to treat influenza and other diseases, non-destructive inspection techniques for buildings, bridges, and other structures. These are just a few of the applications of particle accelerator technology. Further progress in research for the ILC should mean further progress in technology in these and other fields.
I was fascinated to hear that if the ILC project goes forward, it would draw 10,000 researchers and their families from around the world and present a chance for Japan to globalize at home.
There are still a lot of issues to address for Japan to create a city for a large overseas population to live in over a long period.
Today we've looked at plans for the International Linear Collider. It's an important subject, not just for the future of science, but for the future of Japan more broadly.
We want to keep tabs on how the ILC plan is taken up in Japan and how the project moves forward.
That's all for Science View. See you next time.
Sakura is located in Hyogo Prefecture, which is in West Japan. It's a rectangular 700-meter-long facility, and the whole thing is one giant microscope.
So this microscope that allows us to see 1/1000th of a millimeter